Hello viewers, welcome to CEC lectures. Myself Dr. Preeti Jagmani from Department of Computer Science, Aribhat College, University of Delhi. So in the series of operating system, in the previous lecture we were dealing with deadlocks, and in previous lecture we have seen the modification of resource allocation graph in order to avoid the deadlock. And today's agenda is about the banker's algorithm, or today's agenda is banker's algorithm. So let me begin with this. This is also a tool for, or this is also an algorithm for avoiding the deadlock. And how are we going to do it? Let's see it. So banker's algorithm, as you can as you can see by the name, banker's algorithm, it is something related to banking system. Why it is this algorithm has been given such a name that it resembles to a banking scenario. Now let us consider what is that scenario. Let's say in a bank I'm taking a very small example for the sake of simplicity. In a bank I am having, let's say, kind of 100 rupees in total in cash, and there are some account holders, let's say kind of 5 account holders into that in that bank, who all have deposited money into their accounts, and that total money of all those 5 people or all those 5 accounts gives a total of, let's say, 75 rupees, and the total cash available in the bank is 100. Now a person walks inside the bank and asks for a loan of, let's say, 50 rupees. Can I give that loan? No. Why I cannot give that loan? Because in the scenario, if all the account holders comes to withdraw their money, then bank will not be able to give them money if the loan is already given. So this banker's algorithm is used in the banking system in order to check that whether a loan can be sanctioned or not, and it depends on what is the state of the bank with respect to current money, what it is having, and what the account holders can request. So the bank would never allocate its money in such a way that it can no longer satisfy the needs of all its customer. So that essentially means, now if I am going to connect this with the previous concept of safe state, that means if bank is not sanctioning the loan, that means it is no longer, it will not be in a situation to satisfy the need of all its customer. That means bank is trying to be in a safe state always. So now coming from the scenario of bank to the scenario of system. Now let's say we have a system with limited amount of resources or limited number of resources, and let's say we have 2 we can say processes there already, which are P1 and P2, and P1 and P2 are requiring some resources obviously, and there comes a new process, let's say P3, and it is also requiring some resources. Now if I can say that after giving all the resources up to their requirement to P1 and P2, I'll be checking whether my system will exist in the safe state, then only I will be able to give or able to serve the process P3, or I will not serve the process P3. Now how are we going to maintain such a huge such a complicated accounting? Just by ensuring that when a new process enters the system, it must declare the maximum number of instances of each resource type that it may need during the whole process of its execution. That means right from entering up to the termination, whatever requirement a process is going to kind of foresee, or a process is going to have, those maximum number of instances of each resource type must be declared well in advance, and this number must not exceed the total number of resources in the system. And when a user requests, or when a process requests a set of resources, the system will determine whether the allocation of these resources is going to leave the system in a safe state, yes or no. So, if there is going to be a safe state even after allocation or of the resources to a user, or even after fulfilling the request of a user, the system will still be in the safe state, then the resources are allocated, otherwise the process is going to wait unless some other process is going to release enough resources. Now, this whole calculation is what you called, or this whole strategy, this whole technique is called Banker's algorithm. Now, how are we going to perform this Banker's algorithm is with the help of some data structures, then we have some algorithms, and then we will run those algorithms as and when the situation comes in. So, let us try to understand that. Now, let us say here is a number of processes and there are some number of resources. Now, one advantage of this Banker's algorithm is that it will also work with the situation when the resources are having multiple instances of each resource is having some multiple instances, or some resources are having multiple instances. Please recall that our previous tool, which was modification of resource allocation graph, that tool was only applicable in the scenarios when each resource is only having one instance, but here the Banker's algorithm will be applicable to the scenarios where resources may have multiple instances. Now, let us say the n is the number of processes in the system and m denotes the number of resource type, and there can be multiple we can say multiple instances of each resource type. Now, here we will be requiring some data structures, or basically we can say we will be requiring some arrays. These are arrays, the data structure which is being used here. Now, what are the data structures which we are going to use in Banker's algorithm? One is the array available. This is an 1D array of size m, indicating the number of available resources of each type. For example, I am having available of j is equals to k, means there are k instances of the resource type rj. For example, I am having 3 resources. One is, let us say, printer, another one is a tape drive, and third one is, let us say, kind of some storage, another storage device. So, if so here the value of m is 3. There are total 3 type of resources, and now if available of 0 or available of 1, we can say, which is printer, is let us say 3, that means we are having 3 instances of each resource type rj, which is printer. So, printer is having 3 instances, so we will write 3 in the first we can say cell of the array which is named as available. Another data structure which is used here is the max. Now, this is also an array but of 2D size, and the 2D size is of n cross m, where m is the resource type and n is the number of processes that I have already told you. That now max is a 2D array of size n cross m that defines the maximum demand of each process in the system. Now, assuming max of I comma j is equals to k, that means process pi may request at most k instances of the resource type rj. So, for example, there is a process, let us say p3, that p3, so for example max 3 comma 1, that means the first resource, which is printer, the maximum instances of this printer which can be requested by p3 will be equals to, let us say, k, or let us say that is equals to 5. So, max of 3 comma 1 equals to 5, that means the third process is going to request the first resource maximum k instances, maximum 5 instances of the printer can be requested by that resource. That is what the maximum array is telling us about the maximum demand of each process in the system. Then we have another array, which is the array named as allocation. This is also a 2D array of size n cross m, where n is the obviously number of processes, m resource type, and n is the number of rows here, m is the column. Now this allocation is going to, or this array allocation is going to give us the sense of the number of resources of each type which are currently allocated to each process. So allocation of I comma j equals to k, that means process pi is currently allocated with k instances of the resource type rj. So for example, allocation 3 comma 1 is equals to 2. So third process and the first resource, which is printer, as I have taken the example here, the third process is having 2 instances already allocated of the resource R1, which is printer here. That is what the meaning of the allocation array is. One more data structure, which is array, is named as the need. So need is also a kind of 2D array of same size n cross m that indicates the remaining resource need of each process. So for example, allocation of ij is max of ij, I can say, is 5, allocation is 2, that means the need is 3. So basically we can say need of ij is equals to max of ij minus allocation of ij. So max of ij, that means whatever process has requested in maximum, for example 5 instance of a particular resource. So max of p 3 comma 1 is 5, and 2 of them, 2 printer instances are already allocated. So minus will be allocation of I comma j, which is 3 comma 1, and then we will say 5 minus let's say 3 is 2 are still needed. So basically the array need is 2D array of size n cross m, indicating the remaining resources which are needed by each process. So here we have seen the data structures in this Banker's algorithm, which are: one is the need, whatever need is left, another one is the allocation, what is currently allocated to each process. Then we have seen whatever is their maximum demand, and 1D array of size m, which indicates the number of available resources of each type. So what are we going to do with these 4 arrays, or these 4 type of data structures? So here, as you must have guessed by this time, that we have some availability, we are looking into some maximum demand which is being put in by a process. We are also looking at what is being currently allocated to the process, and also what is the need which is left, I mean how much is the requirement left, we can say. So by taking all these calculations into account, we are going to run 2 algorithms onto this system state, and these algorithms are safety state and a resource request algorithm, and then we will check that whether allocation of some particular resources to a process is going to lead the system into a safe state or an unsafe state. If it is going to lead the system into an unsafe state, we are obviously not going to we can say fulfill that request. If the system even after fulfilling the request will be in the safe state, then we will be taking that. So we have the allocation, which specifies the resources currently allocated to the process. We have need, which specifies the additional resources that the process may still need the request to complete its task. And the agenda is, we also we always try to be in the safe state, and this can be done with the help of 2 algorithms. Now what are these 2 algorithms? First algorithm is the safety algorithm. So, safety algorithm is there to find out whether or not a system is in a safe state, and how are we going to kind of calculate that. Let us say we have two more vectors of length m and n, which is work and finish. So, work is equals to available and finish of I, it is for kind of all the processes. Finish of I is equals to false, that means all the processes are have not finished yet. So, when a process, let us say third process is finished, we will say finish of 3 is equals to true. Now, what are we going to do in this safety algorithm is we are going to check the availability status for each type of the resource such that need of I should be less than equals to work, because work is nothing but the availability, and the need of a particular process of for a particular resource should be less than availability, because we cannot allocate more than what is being kind of available, and we also keep on updating these arrays. So, first of all we will be checking the availability status for each type of the resource by comparing the need and the availability, which is now stored in the work algorithm. Then if we are going to allocate the resource, then that allocation will be added to what is being already allocated. So, for example, let us say we are allocating 2 instances of printer and one is already allocated. So, now the total allocation is going to be 3. So, work is equals to work plus allocation to get the new resource allocation, and also we need to check the status of the resource availability for the next process. And when we are going to let's say finish of I is equals to true, that means the system is safe for all the processes. That means we are kind of allocating the resources and we are checking that the system is still in the safe state. For let us say 1 we have allocated, for P1 we have allocated some resources, the system is in the safe state. So, we will say finish of 1 equals to true. For let us say the second process finish of 2 will also lead the system into the safe state, we will say finish of 2 equals to true. But now with these two allocations already going on, if we have a third request, let us say with P3, and if we are going to calculate the state of the system, this is going to make the system enter into an unsafe state, then we will not say finish of 3 equals to true. We will say finish of I equals to true when the system is in the safe state for all the processes. So, this was about the safety algorithm. One more algorithm which which is going to be very instrumental in case of a banker's algorithm is about the resource request algorithm. This resource request algorithm is going to check about the behavior of the system when a process makes each type of the resource request, and this is going to consider a request matrix. So, when the resource allocation state is safe, the resources are allocated to the process Pi, and if the new state which is going to be there after allocation of the resources to the process Pi is going to lead the system into an unsafe state, we will make the process Pi to wait, and we will come back to restore the old resource allocation state. That means we will not proceed with the resource allocation. So, basically safety algorithm is going to check that whether we can allocate the resource here is going to lead the system into the safe state or not. Similarly, resource request algorithm will check that how a system is going to behave when a process makes each type of resource request, and this will be done in the form of a request matrix. So, basically four we can say data structures. One is available, another one is max, third one is need, and with the help of these two algorithms, which is resource request and safety algorithm, we will determine that even after every allocation, whether my system is going to be in the safe state or in the unsafe state, and then we have we will take a decision that whether this allocation should happen or it should not happen. So, for example of this banker's algorithm, let us consider a system with, let us say, 5 processes starting from P0 through P4. So, P0, P0, P1, P2, P3, P4 and 3 resources. So, the value of M is going to be 3 here. So, M is A, B, C, resource type is A, B, C. Now, the value of the array which is having the resource type. So, for example, A has 10 instances, resource B has 5 instances and resource type C has 7 instances. So, available of we can say the resources is being controlled by this situation, that how many resources these are having. Now, let us say we have let us consider the figure which is available on the screen. I am having the data structures which are available, max and allocation. So, available is going to show what is being currently available, or how many instances of resource A are currently available, 3, of B it is 3 instances, and of C it is 2 instances. What is maximum which processes has declared before the execution? P0 has called for or has declared the maximum requirement of 7 of resource A. For B it has asked for 5 resources, and for C it has asked for 3 resources. Similarly, process P1 has asked for 3 resources of type A, 2 resources of each type B and C. So, here we have the situation, as you can see on the figure, whatever is being declared, whatever is being we can say demanded up to its maximum capacity is given in the max array, and the numbers are itself pretty clear. What is available is given in the available array, and what is already allocated is given in the array of allocation. So, for example, P0 is presently allocated with 1 resource type or with 1 instance of B. P1 is currently allocated with 2 instances of A. P2 is having 3 instances of A and 2 instances of C. Similarly, P3 is having 2, 1, 1, and P4 is having only 2 instances of resource type C. Now, what are we going to do with all these we can say arrays? So, now we will be calculating the need, the array need, which is defined to be, which we have already seen, is max minus allocation. So, max minus allocation, if we can see, so process P0 max is 753 and allocation is 010. So, it will be 743. Then for P1 it is going to be 122, for P2 it is going to be 600, for P3 it is going to be 011, and for P4 it is going to be 443 and 1. And here is the content of the matrix need which is defined to be max minus allocation, and this is as follows. Now, this is what is being needed. Now, what will happen in the system? Presently this system is in a safe state. Now, what will happen, that P1 is going to request 1 additional instance of the resource type A and 2 instances of the resource type C. So, the request is 102, and this is being done by the process P1. So, now the question is of whether we are going to whether we are going to fulfill this request or we are going to make the P1 hold. So to decide that whether this is to be fulfilled or this is to be immediately fulfilled, we can say we need to check whatever is being requested is less than equals to available, yes or no. So request is 102 and the availability as we have seen is 332, we can see here is 332. So apart from this 332, even if we are going to allocate 102, which is a lesser quantity of all the resources, lesser or equal, because C resource is equal here. So request of this resource, request of this process P1 is less than available. So we can, we can say that yes, we can allocate this resource. So now, but also we need to check that after allocation, what will be the situation of the state. So let's say for some time we pretend that this request has been fulfilled, and what is the new state now? So here is the new state, the availability has reduced and allocation has increased. So the availability has now become as 2, 3 and 0, while we have entered it in the need, that 102 has kind of entered as in the need. So now next situation of the following new state in which the system is going to arrive if we are pretending that this request has been fulfilled. So availability has reduced. Now we have 2, 3, 0 as the availability of A, B, C. Now let's say one more request has come up. So one more request has come up and that request is let's say P3. But before ensuring that whether we can immediately grant this request of the process P1, we need to check that whether the new state is a safe state. How are we going to check that whether the new state is safe state? For that we have safety algorithm, and we need to find the sequence that will that satisfies the safety requirement. So when the system is in this state, the request assuming that is in the safe state, and we are moving forward, and there is another what you call this thing, process request for 330. So this cannot be granted because this is more than the availability. We don't have 330 for A, B, C. So whatever P4 is requesting for is more than the availability, so we surely cannot grant it. Now let's say one more request comes up by let's say P0 and it is requesting for 020. Now here in case of 020 being requested by P0, the resources are available, but the resulting state after granting the request of P0 will be an unsafe state. So here these resources will not be granted. So we will be only granting the resources if the new state which will come up after granting is going to be a safe state. Even if we have resources, we will not allocate the resources unless we have the guarantee that the system will be in the safe state. So here in this lecture we have seen Banker's algorithm, we have seen what are the two techniques, which are the two algos which are used inside this technique, which is the safety algorithm and the resource request algorithm. Also we have seen what are the data structures being used for this, and we have seen the whole complete usage taking an example, and we have seen how this Banker's algorithm is going to make the system into a safe state. Here is a list of references which is being used for this preparation of this lecture. Till the next lecture, goodbye, take care.